Hi everyone, I'm Yogadharani, working as Assistant Professor in Department of Computer Science and Engineering at SNS College of Technology. And in this video, I'm going to tell you what is minimum spanning tree with real world problem solving. Mm, So this concept is a blend of mathematical and real world problem solving used in everything from network design to image processing. By this end of this session, students, you are able to not only understand the concept of minimum spanning tree, and it's also called as MST, but also apply it to optimize real world system efficiently. So in this video, I'm going to give a recap of this session, content delivery, activity, and summary based. And recap of the session is yeah, graph, edges, weights, connectivity. So you guys all might know about what is graph. Graph is nothing but a set of vertices which is connected by the edges, and graph types or weighted graph, unweighted graph, directed graph, undirected graph likewise. So, throughout the roadmap of today's session, you guys must understand the MST through the design thinking concept and explore algorithms like um, Kruskal's and Prim's algorithm, and engage with some activity and ended up with a summary. Like now empathize part. Ravi faces a cost challenge, and Ravi is a network engineer at a telecom company, must connect 8 new cities with optic fiber cables. And if he connects cities randomly, cost will skyrocket. If he escapes um, connections, the network breaks. So how can Ravi design the most efficient network? That is where minimum spanning tree comes in. So next I move on to the different one. Here this is our core problem definition. Ravi want to connect all the nodes or cities in such a way that the total cost is the smallest possible, and there are no loops or redundant path. This gives us the three pillars of MST. The pillars are if one graph must be of a minimum spanning tree, that graph should be connectivity to all the vertices, and it must contain the minimum total weight to visit all the vertices, and should not form a cycle. This is the property of a property or a pillar of a minimum spanning tree. And the next activity is make it a practical. I will divide you into groups. So each group will receive a graph representing network of cities, and your jobs to find the minimum spanning tree using either Kruskal's or Prim's algorithm. So think of yourselves as a Ravi's team optimizing a real telecom network. Once done, we will compare results and discuss why different algorithms might still yield the same minimum spanning tree. So next I move on to the immediate part. Now let's brainstorm. Ravi could brute force all possible networks, but that is exponential and impractical. Instead, we use a greedy approach, always choose the cheapest and safe connection that does not create cycle. So as this is our property of minimum spanning tree, the properties are should not form a cycle and should be in connectivity to all the vertices, and it must be of minimum total weights. So this leads to our two famous algorithms such as Kruskal's and Prim's. So Kruskal algorithm is nothing but we build a graph from the edge level, and Prim's is nothing but build from the vertex one. And see the example of greedy algorithm, how greedy algorithm works here, and it splits the answer into the sum. And greedy algorithm is nothing but the optimization algorithm, and it is the cheapest and safe algorithm for visiting all the wedges. And then I the prototype. Prototype we have two algorithms like Kruskal's and Prims. In Kruskal's algorithm is edge centric, and where short all edges by weight and keep picking the smallest one, and that does not form a cycle, and which we check using the disjoint set union and find structure. We should stop when we have got v minus 1 edges. So think of it as connecting the cheapest road between the cities without forming loops. Its efficiency comes from the sorting edge of big O of E log E. And to the Prim's algorithm. Here Prim's algorithm is vertex centric. It begins at any vertex and keep expanding by adding the cheapest edge connecting the current tree to a new vertex. And it's like spreading a network from one city outward, and similar to how a power grid expands. So is a priority queue or a min heap makes it faster, and here efficiency is a big O of E log V. Here see the example. Here nearly 7 to 8 vertices here, and all vertices connect with each other, and we must follow the adjacency matrix and see this example here. Next time, the technical depth of minimum spanning tree. So here minimum spanning tree is not just theory, it powers a practical solution like network design means it building efficient computer, electrical or telecom networks. Likewise in transport planning, designing low cost road or a rail or a pipeline routine. In image processing used in clustering or segmentation, especially in Kruskal's based ML model, and in civil engineering for irrigation or utility layout to minimize material usage. And then I move on to interdisciplinary or future scope. Here, looking ahead, minimum spanning tree concepts are evolving in modern systems like IoT or smart cities. Connections change dynamically, and dynamic minimum spanning tree algorithms handle such updates efficiently. In distributing computing, a parallel minimum spanning tree um, speed up computation across networks and essential for big data and AI infrastructure design. Then summary part. So let's summarize the key like a minimum spanning tree concepts. Connects all nodes with a minimal cost and should not form a cycle. And Kruskal's and Prim's algorithm are the two primary greedy algorithms, and applications extends for beyond computer science from telecom to civil planning. And these are the applications like network design, transportation, image processing, and several other applications of a minimum spanning tree. So this is the mind map of a minimum spanning tree, and it has the two algorithms as I told you earlier, Prims and Kruskal's, and it takes the steps and complexity, and the properties are should be connected to all the vertices and should not form a cycle. It's also called as acyclic graph, and it should be of minimum cost throughout the traversal of a graph. So I catch you in another video. Hope you all understand this concept of minimum spanning tree. Thank you all.